Hi guys, in this part of the video we will do hands-on for the bias variance trade-off that we learned in the previous video. So we will start off with importing the libraries. First library that we need is import pandas as PD, we need numpy as np, we need matplotlib.pyplot as plt. Okay, these are the basic libraries that we need, that we require in each and every project. So in this project basically we will be taking a data set which is already available in sklearn, which is a breast cancer data. So we will say from sklearn dot datasets import load breast cancer. Okay. Once I have the dataset, I'll have to split this dataset into training and testing. So for that, I need from model selection, I need to import train test split. Once I have the data, I'll have to apply the model. So we will see once we look at the data that this is going to be a binary classification problem. And the most basic model that we have for binary classification is logistic regression. So we will import that as well from sklearn.linear model import logistic regression. Once we have applied the regression model, we will have to measure the accuracy. So from sklearn.matrix, we will import accuracy score. Okay. So we're done with importing. The first thing I'll need here is actually the data set. So what we will do is we will load the data set. Okay. So we will load it. In order to load it, we'll have to instantiate it and store it in a variable. Okay. So I'm storing it in a variable called as data. Now let's take a look what is there in data. So see, this is how the data looks like. I can also convert it into data frame, but let's not get into that. Okay, it will be just a little additional steps which we can avoid. So let's understand the data here itself. There's something called as data, there's something called as target. Now let's understand what the target is. So target is very important. So the problem is to classify the tumors as either malignant or benign. Okay, so that's what the target data is all about. It is in zeros and ones because we just have two targets. Okay, so that is why we have binary target. So this is our prediction point. We need to predict whether the tumor is malignant or benign. That is why it is called as target. And we have certain features. Let's see the name of the feature. Okay. So these are the name of the features we have: mean radius, mean texture, mean parameter, mean area. These are the feature names. So feature names, the data about the feature name is stored in something called as data. Okay. So generally, if we follow the convention, what we do is inside X we put the features and inside Y we put the target. So data, what was there in data? Data about the features. Okay. Inside data we have something called as data. So data has the feature data, and data.target will have the data about the target. Okay. So data.target. So basically with this line of code, what we are doing, inside X we are storing data.data and inside Y we are storing data.target. I hope this is making some sense. The next thing we will do is we have the data. Okay, I need to split this data into training and testing. So X train comma X test. I'll have to split both features and target into training and testing. Y train, Y test. Okay. I'll apply train test split. Cool. the first parameter that we want to put. So just press shift tab to see the number of parameters train test split has. Okay, so out of all these parameters, what I will require first is which data are we trying to split, x and y. So those will be the first two parameters. What will be the split of train test, like how many, what will be the percentage of training data and what will be the percentage of testing data. So that we will provide in something called as test size. I want to split it in 70-30 ratio. So our test size will be 30%, which is 0.30. Then I'll have to give something called as random state. Okay, we need to make sure that in each iteration our model has the same set of data. That is why we provide something called as a random state. Then I'll also provide a parameter called as stratify. So what stratify does is it balances out the data. Now what balancing out the data means is, see here we are providing why to stratify. It means I want the target to be balanced. Now what do we have in our target? We have malignant and benign. So just imagine if we have 100 rows of data, and in those 100 rows 90 rows are malignant and only 10 are benign. So this is imbalanced data, right? If we train our model based on this data, obviously whatever the predictions are there will be malignant. So this does not make any sense. So what we are telling our train test split is to stratify the target, that is balance out the target. Okay. Now once this is done, what we want to do is we want to train our model on different model complexities. So I'll have to initialize those model complexities. Okay, so I'll initialize those model complexities in a variable called as C values. So I'll provide some model complexities here: 0 0.001, 0 0.01, 0 0.1, 1, 10, 100. Once I have trained my model on all these model complexities, what I want to do is I want to figure out training and testing accuracy on all these model complexities. So I will define a list called as training accuracy, and I will define a list called as testing accuracy. As and when I have the accuracies for all these model complexities, I'll keep on appending them in these lists. Now I am going to train this model on logistic regression, but the point is I want to train my model on all these model complexities. So I'll run a for loop on this. Okay, for C in C values, I want to train my model. So I'll say model is equal to logistic regression. Now if you want to check the parameters, you can press shift tab and check the parameters you need to apply. Okay. Since I am using the model complexity, that will be my first parameter here. While training the model, we have to give a parameter called as maximum iteration, which will tell our model how many iterations do we want our model to run. So basically, what are the iterations? If we don't provide these maximum iterations here, our model will run n number of times till it finds the best possible solution. So what we are saying here, only run for 1000 times and return whatever result you get. Okay. Then we will provide random state. Random state has the same function as we discussed earlier. Okay. Then we have something called as solver. So with machine learning models, with respect to machine learning models, you might have heard something called as fine tuning. So what fine tuning does is it finds out the best parameters so that we get the best possible solution. So solver is one such thing which finds out the best parameters, and since our data set is small, the best possible solver we can use is liblinear. So I'm using that. Once we are done with the model, I'll fit it on the training data. So X train and Y train. Okay. Once I have fitted the model, it's time for predictions for both training prediction and testing prediction. So I will define a variable called as train pred, and I'll do model.predict. Since I'm predicting for training data, I'll give input X train. Okay. For X train, I want to predict the target. Next will be test pred, model.predict. Since we are doing predictions for testing data, it will be X test. Now we have the predictions, okay. Now I want to calculate the accuracy for both training and testing. So in order to calculate the training accuracy, I will, use this and keep on appending the training accuracy. So training accuracy dot append accuracy score. So how do I get the accuracy score? I will compare this with Y-train, right? Train pred, comma, Y-train. And in order to get test accuracy, I will compare the test accuracy variable with Y-test. Okay. So I believe we are done with this. So once we are done with this, I'll plot this on a graph and show you how the bias variance trade-off looks like. Okay. In order to do that, I'll have to provide the size of the figure. So I'll say fixed size is equal to 7,5. Next, I want to do plotting. On the x-axis, I want model complexity. And where did we store the model complexity? Inside C values. So on x-axis, I will have C values. On y-axis, I will have accuracy score. Okay. So training accuracy I want. First, I want to plot training accuracy. Okay. I want a marker which will be 0. And I want a label which will say training accuracy. Good. The same thing we will repeat for testing data. And this will be testing. Good. I want my X scale. I want my X to be in logarithmic scale. I'll explain you once we have the graph how it looks like. I want my X label as model complexity. Y label as accuracy score. And a title which would say bias variance trade-off. Apart from this, I want a grid to be visible for my graph. So I'll say grid true and I want a legend. Cool. So this is how my graph looks like. I'll explain you each and every term. So this is the title. This is X label. This is Y label. This is called as legend. We said that we want X scale in log. So if you see, this has been spread out evenly. If I comment out this line, I'll show you how it looks like. See, it is not evenly distributed in the way we have defined the model complexity. See, these are the model complexities that we want. Here, the model complexities are totally different. So I'll uncomment this again. Okay. So see, 10 raised to minus 3 is 0.001. This is 0.01, 0.1. This is 1, 10 and 100. Okay. Now if we try to understand this graph, also marker 0 is this. Okay. Marker 0 is this, and this is where the label appears inside the legend. Now blue color is training accuracy. So if we try to understand this, as the model complexity increases, the accuracy score is increasing. And for testing accuracy, as the model complexity increases, the accuracy is increasing, then it is becoming a plateau. So if we want to find out the sweet spot, okay, the sweet spot where the bias variance trade-off is happening, I would say it is between 10 raised to minus 1 and 10 raised to 1. Why? because see, we don't care about the training accuracy here, all we care about the testing accuracy. So if we see between 10 raised to minus 1 and 10 raised to 1, the training accuracy, I'm sorry, the accuracy is increasing and then it is plateauing. So this is my sweet spot. Okay, so this is the bias variance trade-off that we are looking for. Hope you understood this concept. Thank you so much.